Hello and welcome everybody. Today we are looking at factoring polynomial expressions lesson number 4. So we have looked at factoring trinomials through inspection, and this is the same idea, but it's just a bit of a different circumstance. So I will get started and show you what's going on. I think my pen, there we go, is working. So we are looking at what's called difference of squares, and we'll get into that in a second. First, we're going to complete this table. So you've seen a table like this before, and what we're going to do is start at the top row there, and we're going to say that we're looking for two numbers that multiply to 16 and add to -6. So normally we would do our little multiplication chart, and then we would say 1 and -16, -1 and +16, 2 and -8. Oh, there it is right there. 2 and -8 are the integers. 2 and -8. -8 multiplied by 2 is -16. -8 plus 2 is -6. So it works perfectly. If -16 and -6 are those two values, then they sit in our polynomial as the b and c term. This is like the b term and the c term when we're looking at x squared plus bx plus c. And in factored form, we know that we are going to use the integers we just found. X plus 2, x minus 8. So that's kind of everything when it comes to factoring polynomials. We usually start with the polynomial. We find two numbers that multiply to -16, add to -6, and we plug them into the factors there. We're going to do one more. We have -15 and -16. So we're looking for, first of all, let's write our polynomial. It's going to be x squared minus 15x minus 16. And that comes from the sum and the product, the b and the c. So now we're looking for two numbers that multiply to -16 and add to -15, and that's going to be 1 and -16. You could go through your multiplication chart if you wanted to. Luckily, we've already done it. So right here, 1 plus -16 is -15, and 1 times -16 is -16. And that would give us the factors of x plus 1 and x minus 16. So that is a review of the last two lessons, which is awesome. The next three examples are going to be a little bit different. You notice that we have on the next three a sum of 0, something we haven't encountered yet. So it's just, again, another scenario. Then we have to learn how to do a bit of a trick. So you can see that if we have the sum of 0, when we write our polynomial, that becomes plus 0x in the middle. That middle term is multiplied by 0, so it ends up disappearing. And what we're left with is x squared minus 16. Super weird because it's not a trinomial, or it doesn't have three terms. We're used to looking at a polynomial with three terms and splitting it into the two factors, like we did in the first two examples. But we can still proceed and find the two integers that multiply to -16 and add to 0. Let's continue our -16 chart. -2 and 8. 3 doesn't go, but how about 4 and -4? Yeah, sorry, I just had a sneeze. Yeah, that works, right? Because -4 multiplied by +4 is -16, and 4 plus -4 add to 0. 4 and -4. That means that our factors are going to be x plus 4x minus 4. That's kind of cool. Let's try the next one. So we're looking for two numbers that multiply to negative 64 and add to 0. If we were to write that polynomial, x squared plus 0x minus 64, and that middle term ends up canceling, so we're left with x squared minus 64. This is what you would see if you got a question that said factor this. You would see what looks like what is a binomial, and you're used to seeing a trinomial. So there's kind of a cool trick here. But anyways, we need two numbers that add to 0 and multiply to negative 64. I'm not going to create the multiplication chart because it does get quite long for 64, but how about positive 8 and negative 8? They both add to 0, and when I multiply them, they multiply to negative 64, so that I get x plus 8, x minus 8. So you can start to see a bit of a pattern here. In the last two examples, we're using the same values, but with just a different sign. So we have our factors are x plus 4 and x minus 4. And then again, in the last example we did, we have x plus 8 multiplied by x minus 8. So let's try the last one. Two numbers that multiply to negative 25 and add to 0. So our polynomial is going to look like x squared plus 0x minus 25. So we don't actually have to write that middle term because 0 times anything just is 0. So we end up with x squared minus 25. So two numbers that multiply to negative 25 and add to 0. You've probably guessed it already. 5 and negative 5. They're going to be the same number. One's just going to be a negative. So we have x plus 5, x minus 5. So if we use that pattern that we just saw in the last three examples, we can do a few questions here. So we know we have an x squared. So we have x squared minus 9. We know we have an x squared. And now we're looking for two numbers that multiply to negative 9 and add to 0. Well, how about 3, positive 3, and negative 3? Positive 3 and negative 3. How about the next one? Oh, wait, we should check that. Let's check just in case. We'll FOIL. X plus 3 multiplied by x minus 3. I'll just do it off to the side here because I don't think I have enough room. So let's FOIL. First, outside, inside, last. So the first is going to be x squared, x times x, outside. X multiplied by negative 3 is negative 3x. Inside, positive 3 multiplied by x, plus 3x. And last, positive 3 multiplied by negative 3 is negative 9. And you can see those two middle terms are going to cancel. Negative 3x plus 3x is 0x. So we are left with x squared. What is happening? X squared minus 9. And that's what we started with. So we did it right. Same process with the next one. X squared minus 49. So I'm looking for two numbers that multiply to negative 49 and add to 0. Put an X at the start. So multiply to 49, add to 0. Most likely going to be the same number because that's the pattern we've been getting. But one negative, one positive, obviously. So what times what is equal to 49? 7 times 7 is equal to 49. So let's say plus 7 minus 7. I think we're starting to get it a bit. Let's do this one here. I have a squared minus 100. So I'm looking for two numbers that multiply to 100 and add to 0 because that middle term is gone. Well, we know that 10 times 10 is 100. And if I had positive 10 and negative 10, that would multiply to negative 100, and that would add to 0. Plus 10, negative 10. So hopefully you're starting to see the pattern there. What I'm going to do is I'm going to skip to the next page and introduce to you this topic. This is called a difference of squares. So you see here that we've been dealing with, so when we first started factoring trinomials, we were dealing with x squared plus bx plus c. But in these special cases, these difference of squares, the b value is 0, so we don't actually end up getting a middle term. We get x squared plus c, which is okay. We can still factor that because we can learn this difference of squares here. So the big thing is that we are dealing with two, so basically we're dealing with a binomial where both terms in the binomial are perfect squares. So we need to do a little review on what a perfect square is. A perfect square is a number that can be square rooted, or two numbers that when it's multiplied by itself becomes a perfect square. This is why I hate definitions. So 2 times 2 is 4. 4 is your perfect square. Perfect square. 3 times 3 makes 9. So that's a perfect square. Don't forget about 1 times 1. 1's a perfect square. 4 times 4 is 16. 16's a perfect square. So what are the other ones? 5 times 5, 25. 6 times 6, 36. So on and so forth. What about x squared? X squared is a perfect square because it is x times x. It's x multiplied by itself. What about x to the power of 4? That's a perfect squared because you can say it's x squared multiplied by x squared. So all of these here are perfect squares, and then I accidentally flipped it, but that's okay. So whenever we have two perfect squares in our binomial and a subtraction, we can write the terms that are factor it into a minus b multiplied by a plus b. I'm going to skip this bit here. I think this is confusing, but it will confuse you. But what we're going to do is we're going to take this idea and I'm going to do some examples, and I think this will help. So whenever we have a squared minus b squared, we can factor that into the square root of a plus the square root of b, the square root of a minus the square root of b. So whenever you get to a binomial and it says factor, what you want to do is check, is my first term a perfect square? Well, we know a squared is a times a. What about my second term? Is my second term perfect square? Well, I can get 4 by doing 2 times 2. And there's a subtraction. There always, always, always has to be a subtraction. So whenever that's the case, we can split those into two factors where we have a plus 2 in one and a minus 2 in the other. All right, the next one, t squared is t times t. 144 is 12 times 12. One's positive, one's negative, and we're done. Both of those numbers are perfect squares, right? T squared is t multiplied by t, and 144 is 12 multiplied by 12. Next one, x squared minus y squared. Well, x squared is a perfect square, x times x, and y squared is a perfect square, y times y. One will be negative, one will be positive. As long as one's negative and one's positive, the order doesn't matter. This one's weird. They just show it as a 7 squared. Normally that would be p squared minus 49 because 7 squared, 7 to the power of 2 is 49. But 7 to the power of 2 is also 7 times 7. So the first term, p squared, is a perfect square, p times p. 7 squared is obviously a perfect squared because it's 7 multiplied by itself twice. One's a plus, one's a negative, and we're done. So it seems really straightforward, but the hardest part with difference of squares is that people don't tend to recognize that the question is a difference of squares because it won't say on tests or anything, factor the following polynomial using the difference of squares method. It's up to you to recognize, oh, hey, look at that. T squared is a perfect square. 144 is a perfect square. I can split those. So there's also a little note down here that says it's not possible to factor a sum of squares where we have a positive value, x squared plus 4, because you can't find two integers whose product is positive and whose sum is 0. This trick only works if it was x squared minus 4. Okay, let's carry on. So we just learned that a squared minus b squared is equal to a minus b multiplied by a plus b, but a squared and b squared can be numbers or variables or combinations of the two. As long as they're perfect squares, this works. So the example here they have is 4x squared. Actually, let's underline here. I think it'll be good to color code. 4x squared minus 25. So the first term, 4x squared, is that a perfect square? Well, 4 is a perfect square, and x squared is a perfect square. And we can get that by multiplying 2x by 2x. So we can write 2x as the first term in both, and then 25 is a perfect square. It is 5 times 5, so plus 5 minus 5. The trick there was we had more than just x squared in the first term. N m squared, oh, I thought I had my highlighter on. N m squared is a perfect square. It can be written as 3m multiplied by 3m. So we'll plug those in here. And for n is a perfect square. It can be written as 2n multiplied by 2n. So we'll go plus 2n minus 2n. And that's that binomial factored. Those are the two factors right there. So again, the hardest part is recognizing that you're dealing with perfect squares or difference of perfect squares. So the first one here, A, 16t squared minus 49. Is 16 a perfect square? 4 times 4, perfect. Is t squared a perfect square? T times t. Is 49 a perfect square? 7 times 7. So 16t squared can be written as 4t multiplied by 4t, and 49 can be written as 7 multiplied by 7. So it's just a matter of splitting those into factors, 4t plus 7 and 4t minus 7. What about the next one? 81a squared minus 1 is the first term a perfect square. 81 is 9 times 9, which is perfect, and a squared is a times a. So we can split that first term into 9a and 9a. The second term, 1, is 1 a perfect square? This one throws people off quite a bit, but 1 is a perfect square because 1 times 1 is 1. So 9a plus 1 and 9a minus 1. What about the next one? 100 minus y squared. Is the first term a perfect square? Yeah, 10 times 10. Is y squared a perfect square? Yep, y times y. So now we can split that into the two factors. We'll have 10 plus y and 10 minus y. Hopefully that starting to make a little bit of sense. D is 36p squared minus 25q squared. So let's start with the first term, 36p squared. 36p squared can be 6p multiplied by 6p, right? 36 is 6 times 6, and p squared is p times p. 6p multiplied by 6p. 25q squared is also a perfect square. 25 is 5 times 5. Q squared is q times q. So we can say minus 5q plus 5q. The next one, 4x squared plus 25. Is our first term perfect square? Yes. 2 times 2 is 4, and x times x is x squared. Is our second term a perfect square? 25 is 5 times 5, so yes. Last question. Is it subtraction? You notice we have subtraction in all of them, and that's important. It doesn't work if there's not a subtraction. And look, we have a plus. So if the question said factor this, we can't pull out a greatest common factor, and we can't use difference of squares because there's a plus. So this is not possible. That's as factored as that's going to get. The last one, 64 minus 9a squared b squared. Is the first term a perfect square? 64 is 8 times 8. So yeah, that is a perfect square. 9a squared b squared. Well, 9 is 3 times 3. A squared is a times a, and b squared is b times b. So 9 is 3 times 3. A squared is a times a, and b squared is b times b. We make one positive, one negative, double check that we still have a negative sign up there, which is good. And we're done. A plus 3ab multiplied by 8. 8 plus 3ab multiplied by 8 minus 3ab. And if you're unsure, how can you double check if this is correct? Well, you FOIL it, right? You do your first, outside, inside, last. That's not last. What am I doing? Last. And you expand that, and then if you get the same polynomial that you started with, then you know things are, all right, you've done things right. I think that's as far as I'm going to go with that. It is a bit of a confusing topic, but it's just you have to remember that when you have up here a squared minus b squared, you can split that into a minus b, a plus b. Difference of squares. Both terms have to be squares, and it's a difference, so there needs to be a subtraction. Cool. Thanks for watching.